start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Challenger.
On the morning of January 28, 1986, 7 astronauts boarded the Space Shuttle Challenger. School children watched from classrooms, reporters gathered with cameras, and millions of Americans tuned in for what was meant to be a routine launch. 73 seconds after liftoff, the sky erupted. A white flash, a twisting trail of smoke, and then silence. The shuttle disintegrated in midair, killing everyone on board. By 1986, shuttle launches had become familiar. Challenger was NASA's 25th mission, and this one had a special passenger, Krista McAuliffe, a schoolteacher from New Hampshire selected to be the first civilian in space. It was supposed to inspire a generation, but behind the cameras, behind the pride, something small was already failing. Something just 11 millimeters thick, a rubber ring buried deep inside the shuttle's solid rocket booster. The booster was made in segments. Between each segment there were joints, sealed by O-rings. Simple rubber loops meant to keep hot gases from leaking out during launch. They were never designed to take center stage, but that morning, the temperature was just 36 degrees Fahrenheit, far colder than any shuttle launch before. The rubber O-rings made of a synthetic elastomer had become stiff, less flexible, and when the rockets ignited, the pressure forced hot gas through a microscopic gap that shouldn't have been there. At T plus 0.678 seconds, a puff of black smoke was seen near one of the joints. Engineers noticed it, but the shuttle continued to climb. Unknown to the crew, hot exhaust was slowly eroding the O-ring, cutting through layer by layer. At 37,000 feet, the final layer gave out. A jet of flame burst through the side of the booster, igniting the massive external fuel tank. The Challenger didn't blow up in the traditional sense. It was torn apart by aerodynamic forces. There was no escape, no way out. Here's the tragedy within the tragedy. Engineers had warned about this exact failure. Morton Thiokol, the contractor who made the boosters, had seen O-ring erosion on earlier missions. In fact, the night before the launch, engineers pleaded with NASA to delay, citing the cold temperatures as a risk. But under the pressure to meet schedules, the warnings were dismissed. One engineer later said, "We were appalled. We were talking about lives." The O-ring failed for a simple reason. Rubber becomes brittle in the cold. Below a certain temperature, known as the glass transition point, polymers like this lose their elasticity. They don't seal, they don't flex, they crack. And this wasn't theoretical. NASA had data showing the risk, but ignored the pattern. The materials told a clear story, but no one listened. The Rogers Commission, launched by the government, confirmed the cause: O-ring failure due to cold temperatures and flawed design. The Commission's most chilling quote came from physicist Richard Feynman, who demonstrated the problem with a simple cup of ice water.
And I put it in ice water, and I discovered that when you put some pressure on it for a while and then undo it, it maintains, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, and more seconds than that, there's no resilience in this particular material when it's at a temperature of 32 degrees. I believe that has some significance for our problem.
He dipped a piece of O-ring material in and showed how brittle it became in seconds. His conclusion? For a successful technology, reality must take precedence over public relations. 7 people lost their lives that day. Not because of a grand explosion, not because of sabotage, but because of a rubber ring, a missed warning, and a system that puts schedule over safety. In engineering, failure is often a chain, never just one mistake. But sometimes all it takes is one overlooked material on one cold morning.